22.4 Analysis Model. Particle in a field. Electric. Today we will cover several key topics related to electric fields. We will start with a broad introduction to the concept of field forces. Next, we will formally define the electric field vector, denoted by the letter E, and discuss how to calculate the electric force acting on an arbitrary charge placed within this established field. From there, we will explore the specific equations used to determine the electric field generated by individual point charges. We will then introduce the superposition principle, which is essential for calculating net fields produced by multiple source charges. Finally, we will apply these theoretical concepts to practical examples, including analyzing a suspended water droplet and determining the field of an electric dipole. In physics, forces are broadly categorized into contact forces and field forces. The gravitational force and the electric force are classic examples of field forces. Field forces are unique because they can act through empty space, producing a physical effect even when there is no physical contact between the interacting objects. We can model this interaction as a distinct two-step process. In the first step, a source particle establishes a field in the surrounding space. In the second step, another particle enters and interacts with that established field, and consequently experiences a force. This slide illustrates the two-step process for field forces. On the left side of the figure, we see a positively charged object, referred to as the source charge. This source charge establishes an electric field in the space around it. To detect this invisible field, we place a second, smaller charge, known as a test charge, at a specific point, P. When the test charge is placed there, it experiences an electric force, labeled F sub E. It is critical to understand that the test charge serves merely as a detector. Its presence is not necessary for the electric field to exist. The field is already established by the source charge. We define the electric field vector, E, at a specific point in space as the electric force, F sub E, acting on a positive test charge placed at that point, divided by the magnitude of that test charge, Q naught. Because force is measured in newtons and charge in coulombs, the SI units for the electric field are newtons per coulomb. The direction of the electric field vector is defined as the direction of the force that a positive test charge would experience if placed in that field. Note an important condition. The test charge must be small enough so that it does not disturb the original charge distribution responsible for creating the electric field. If an arbitrary charge Q is placed in an established electric field E, it experiences an electric force given by the equation F sub E equals Q times E. The sign of the charge dictates the direction of this force. If Q is positive, the electric force acts in the exact same direction as the electric field. If Q is negative, the resulting force and the field are in opposite directions. Caution is needed when applying this equation. It is strictly valid only for a particle of charge Q, meaning an object modeled with zero size. For a charged object of finite size, the electric field might vary over the object's dimensions. Let us examine the electric field created by a single point charge. Consider a test charge Q not placed at a distance r from a source charge, Q. According to Coulomb's law, the force exerted by Q on the test charge is Coulomb's constant, K sub E, times the product of the charges divided by r squared, in the direction of the unit vector r hat. Using our definition of the electric field as force divided by the test charge cancels out. The electric field created by the point charge is K sub E times Q divided by r squared times the unit vector r hat. Here, r hat is a unit vector directed from the source charge toward the point of interest. This figure summarizes the electric field direction relative to the sign of the source charge. For a positive source charge, the electric field points radially outward from the charge. This occurs because a positive test charge placed nearby would be repelled and pushed away. Conversely, for a negative source charge, the electric field points radially inward toward the source. A positive test charge placed in this field would experience an attractive force directed toward the negative source charge. In both scenarios, the magnitude of the field is governed by the inverse square law, scaling with 1 over the distance squared. To calculate the net electric field at a point P due to a group of multiple point charges, we apply the superposition principle. We calculate the individual electric field vectors produced by each independent point charge, and then we add them together vectorially. This superposition follows directly from the vector addition property of underlying electric forces. Mathematically, the total electric field is the vector sum over all individual charges. For each term in the sum, r sub I is the distance from the ith source charge to point P, and r sub I hat is the unit vector directed from that specific source charge toward point P. Consider this scenario. A test charge of positive 3 microcoulombs is placed at a point P, where an external electric field is directed to the right with a magnitude of 4 times 10 to the 6th newtons per coulomb. If the test charge is replaced with a different test charge of negative 3 microcoulombs, what happens to the external electric field at point P? Does it remain unaffected, reverse direction, or change unpredictably? The correct answer is that the field is completely unaffected. The external electric field at point P is created by other source charges in the environment. Changing the test charge changes the force experienced, but it does not alter the underlying field itself. In this example, a water droplet with a mass of 3.00 times 10 to the negative 12 kilograms is suspended at rest in the air. An atmospheric electric field of 6.00 times 10 to the third newtons per coulomb points vertically downward. We model the droplet as a particle in equilibrium, so the sum of the vertical forces must be 0. The electric force must act upward to balance the downward pull of gravity. As the electric field points downward, but the electric force must be upward, the droplet must carry a negative charge. Setting the magnitudes equal, we find that the charge Q equals negative m times g divided by the electric field E, resulting in a charge of negative 4.90 times 10 to the negative 15 coulombs. Here, we calculate the electric field due to 2 point charges, Q1 and Q2, located on the x-axis at distances a and b from the origin. We need to determine the components of the net electric field at point P, located at coordinate 0, y. First, we calculate the magnitude of the individual fields E1 and E2 using Coulomb's law, where the distance squared is a squared plus y squared and b squared plus y squared, respectively. Next, we break these vectors into their x and y components. Following the superposition principle, the total x component is the sum of the individual x components, and the total y component is the sum of the individual y components, accounting for the trigonometric angles phi and theta. We now evaluate a special case known as an electric dipole, where the two charges have equal magnitudes but opposite signs, and are placed equidistant from the origin, so A equals B. Due to the symmetry of this configuration, the vertical y components of the two electric fields point in opposite directions and cancel each other out entirely, leaving E sub y equal to 0. The horizontal x components, however, point in the same direction and add together. Using geometry, the cosine of theta is a divided by the square root of a squared plus y squared. Substituting this into the summed x components gives a net electric field along the x-axis equal to k sub e times 2 aq divided by a squared plus y squared to the 3/2 power. Let us examine the electric field of the dipole at a distant point P, where the distance y is much greater than the charge separation distance a. Because y is very large, the a squared term in the denominator becomes negligible compared to the y squared term. By ignoring a squared, the expression for the electric field simplifies to k sub e times 2 aq divided by y cubed. This demonstrates that at distant points, the electric field of an electric dipole varies proportionally to 1 over the distance cubed. This field strength drops off much faster than the 1 over r squared field of a single point charge. This rapid decrease occurs because the fields generated by the equal and opposite charges largely cancel each other out at great distances. Let us review the main concepts. The electric field is defined as the electric force on a test charge divided by the magnitude of that test charge, with units of newtons per coulomb. Consequently, a particle with charge q placed in a field E experiences an electric force equal to q times E. A single point charge creates an electric field that is proportional to its charge and inversely proportional to the square of the distance from it. For multiple charges, we use the superpositional principle, which states that the net field is the vector sum of the individual fields. Finally, the electric field generated by a dipole falls off proportionally to 1 over the distance cubed at large distances. We conclude with 2 review questions. First, why is it critical that the test charge q naught used to define the electric field be very small, and what might happen if it were large? A large test charge could exert enough force to disturb the source charges, moving them and thereby altering the very electric field you are trying to measure. Second, if a negatively charged particle is placed in an electric field that points straight down toward the ground, in which direction will the electric force act on the particle? Because the particle is negatively charged, the electric force acts in the exact opposite direction of the electric field, so the force will point straight upward.